uh, once video is completed, then we will have the session open for any kind of discussion. And today's lecture is very important because we'll be exposed to the PHL. Okay, so this today's lecture, whatever we learned so much in previous various classes, so all things will be included today, and PHIL hardware setup will be there. So there you will be exposed to various components of a real-time implementation of DC microgrid. So please listen carefully, and then sir will discuss the various important aspects of this lecture. Thank you.
A very good morning. Welcome you, dear students, to the course on Smart Grid, Basics to Advanced Technologies. Today we are going to cover Module 11, Lecture 5, on demonstration of grid-connected DC microgrids. Now, as you could see, a typical architecture of a DC microgrid. You must have heard about DC microgrids, AC microgrids, even for some extent hybrid microgrids, a combination of both. Now, in case of a DC microgrid, all the loads and generations are connected to a DC grid. Am I right? So, if you closely look into the PV panels, those are connected to your DC bus, and even for some extent, the DC loads such as electric vehicles or e-mobilities, they are connected to DC bus. And we do have DC-DC converters connected to storage devices, which also cater to my DC grid. However, we can also see an AC grid which caters the AC loads. And probably this is a system which is a typical AC-DC microgrid, but will focus mainly on DC microgrid component of an architecture. A typical DC microgrid consists of a DC bus, but you cannot have a system of low voltage network which is purely DC in nature. So we need to have a DC and AC bus together. So a typical DC microgrid within a AC-DC microgrid will have both DC bus as well as AC bus. The DC bus is for the interfacing DC sources such as batteries, ultra capacitors, and also cater to some of my DC loads. And in case of AC bus, it perhaps engage all AC sources and also cater your AC loads. Now, the DC microgrid can be able to operate in three different modes. The number one is grid tied, islanded, and autonomous. And perhaps we'll try to focus mainly on grid tied as well as islanded mode of operation. And from the above figure, we can see there are two switches, switch 1 and switch 2. Those are closed at its initial stage. The DC microgrid is under grid connected mode of operation. What I wanted to tell you, after looking into two switches SW1 and SW2, based on its switching on and off positions, the structure or the architecture of this grid may behave differently. From the figure, if both SW1 and S closed, then the DC microgrid is under grid connected mode of operation. However, if S1 is closed and S2 is open, that represent DC microgrid is under islanded mode of operation. It serves DC, AC, and PCC loads. But in case of SW1 is open and SW2 is open, either closed, the DC microgrid is under autonomous mode of operation. So there are three different mode of operation can be experienced through different switching of SW1 and SW2. Moreover, the DC microgrid can be controlled in different layers, such as zero level control, primary level control, secondary level control, and tertiary level of control. In the zero level control layer, mostly grid-tied inverter variables are controlled. At this level, the control response should be very fast and in the range of microsecond to milliseconds. In case of primary level control, the control system contains zero level control and is additionally equipped with grid support and automatic load sharing functions. At the secondary level of the control layer, the control system is equipped with microgrid synchronization, voltage, and frequency control functions. The control response, primary and secondary level control layers are dynamic in nature and slower than the zero level control layer. The tertiary level control layer consisting of optimization algorithms to optimize the power flow, stability, and the DC microgrid cost optimization and its operation. Till now, we have seen the operating modes of the DC microgrids. Now we'll try to understand or try to explore the critical features of the DC microgrids. The slide shows the features and various functionalities of the DC microgrid. The significant features of DC microgrid are grid support, flexibility, scalability, and stability. Let's look into those features one by one carefully. In the grid support, the DC microgrid is capable of providing ancillary services. In flexibility, the DC microgrid is able to reconfigure the system online during faults by disconnecting from the main grid. The DC microgrid improves the overall system stability by providing sufficient stability margin, steady state, and transient operation modes. Further, the DC microgrid increases the system scalability by seamlessly adding more power units. Apart from the features of the DC microgrid, the major functionalities of the DC microgrid are grid voltage and frequency support, coordinated voltage forming and load sharing, harmonics attenuation, energy management between grid and microgrid, serving critical loads during grid outages, and so and so. Though we have discussed during the slide, but just for your more attention, I thought that it would be good to repeat again for your better understanding. Furthermore, the DC microgrids are able to work in normal as well as abnormal conditions. This slide shows the block diagram of the L-filtered grid-tied DC microgrid. In this slide, it is shown that the hardware test bed is developed by interconnecting various components. The AC side of the inverter is connected to the AC grid through L filter. The point PCC shown in the block diagram forms an AC bus where the AC loads are connected. A Hall effect voltage and current sensor are used to measure the voltage at PCC and current through the inductor. The measured voltage and currents are biased to shift the signals above zero level. The offsetted outputs of current and voltage sensors are given analog to digital converter, pins of DSP Launchpad TMS 320 F28379D. Inside the DSP controller, the ADC pins read the three-phase currents and voltages along with the DC link voltages. By using Klux transformation, the ABC components can be converted to alpha beta components. Further, the control logic generates modulation voltages for generating PWM pulses through EPWM pins of the DSP. This slide shows the control logic used for interfacing the DC microgrid with the AC grid. The DC bus voltage controller PI regulates the DC bus voltage at the reference value and generate the AC power reference value. Active current reference is generated from AC power reference as the inner controller requires a current reference. The obtained AC current reference is converted to the stationary reference frame, and this current reference is compared with the measured current, which gives an error to us. The error is further processed through proportional plus resonant controllers, so-called PR controllers, for generating required modulation voltages. The modulation voltages are used for SPWM generation through EPWM pins of the DSP. For switching converters switches, they are mainly IGBTs. The control variables of the PI controller and PR controller can be obtained through proper tuning, ensuring that the stability margin should be more. The slide shows the block diagram of the hardware test bed, and in this hardware test bed, the DC microgrid behavior is emulated through a power amplifier by configuring it with Opal RT. In the Opal RT, the DC microgrid is simulated, which contains PV, battery, and variable DC load. The scaled down DC bus voltage is given to the analog input of the power amplifier. The current fed to the power amplifier is further given to the analog input of the Opal RT. This creates a PHIL loop between the Opal RT and the power amplifier. The combined operation of the Opal RT and the power amplifier emulates the DC microgrid behavior close to perfection. The behavior of the AC grid is mimicked through Synergia programmable grid emulator, in which Semicron three-phase IGBT based PWM inverter is used as a bidirectional DC-AC converter between the DC bus and the grid. The control logic shown in the previous slide is implemented in the DSP controller. The floating point Texas C2000 DSP controller of TMS320F28379 Delfino type is used in this hardware test bed. Now, when you move to the demonstration, hardware demonstration of the same configuration, in this module, we are very much interested in showing the grid integration of the DC microgrid only. The hardware demonstration of energy management using a DC microgrid will be discussed in the upcoming modules. Let us have a look at the test bed of a grid connected DC microgrid. To avoid complexity in the system and for simple understanding, we emulated a DC microgrid through a power amplifier by configuring it through an Opal RT. How to configure the 4-quadrant power amplifier through Opal RT for emulating as a DC microgrid will be discussed in detail in the upcoming energy management scheme module. In this module, the primary intention is only to show the grid integration of the DC microgrid. For this purpose, we assumed the DC bus voltage of the DC microgrid was quite stable and had surplus power to feed to the AC grid. Let us look closely at the overall hardware test bed we developed in the laboratory for your ready reference. Here, the hardware setup shown is used to demonstrate the grid integration of the DC microgrid. This hardware setup is developed by interconnecting various components such as grid emulator, DC bus emulator, DC load, semicron converter stack, filters, and AC loads. The DC bus is emulated through a power amplifier and is connected to the DC side of the semicron converter stack. The AC side of the semicron converter stack is connected to the grid emulator through the filter with the help of miniature circuit breaker, so-called MCB. Voltage and current sensors are used to measure the voltage and currents of the AC bus and DC bus in the DC microgrid. The measurements are given to the DSP controller for processing and PWM pulses generation to control the converters. Let us discuss the hardware setup in component wise. First, we can concentrate on the grid emulator. This is a multifunctionalities equipment, can be used as a grid emulator, electronic load, battery emulator, and PV emulator This equipment will act as an interface between the distribution system and the equipments under test. During grid integration, the power feeding to the grid emulator is sent it back to the distribution system. During power consumption, it draws power from the distribution system, and this equipment can be configured through a working mode switch to operate it in either AC or DC mode. If the working mode switch is at AC mode, the equipment can be used as an electronic load and grid emulator. Similarly, if the working mode switch is at DC, the equipment can be used as a DC source, battery emulator, PV emulator, as well as programmable DC loads. The various functions this equipment switches from left to right, the switches are numbered from 1 to 4. Let us see how to configure various functions of this device. Initially, the device working mode switch at 1. This represents the operation mode of the device is DC. By configuring 4 switches, functioning of the device can be modified. After configuring it in a DC mode, the switch combination decide various functions such as DC source emulator, DC programmable load, battery emulator, and PV emulator. In this video demonstration, we are very interested in showing how to configure it as an AC grid emulator too. For configuring it as a 3-phase grid emulator, the combinations of switches are: switch 1 at one position represent grid emulator, switch 2 at one position represent the equipment under test is on, switch 3 at 0 position represent the 3-phase that can be independently controlled, and switch 4 at 0 position represent it gives bipolar signals. For configuring it as single phase mode, the only change is switch 3 should be at one position. After configuring it as a grid emulator, the values of the voltage can be entered in two ways: by entering the 3-phase voltage values manually in touchscreen. Other way is controlling this device through a GUI or user interface mechanism. The shown window represents software which act as an interface between the grid emulator and user through Ethernet communication. This user interface allows controlling grid emulator voltages in real time without touching the physical device. Desired voltage values need to be entered at 3-phase in the AC operation section of the software. Apart from just entering desired voltage values, it is also possible to monitor grid voltages during experimentation. After entering desired voltages in AC operation, the voltage and current limits need to be specified at the limit section to ensure the safe operation of the system, or indirectly you do not allow this to exceed the operation voltage that you desire it to happen during the experimentation. After entering the desired voltage values and limits, these steps need to be followed to turn on the device output. The first step is to enable the device, which pre-charges the DC link inside the device. After pre-charge, the device is ready to use. Clicking on the run button gives desired voltage at the output point of the device. The grid emulator is connected to an MCB, which is the point where the inverter is connected through an inductor. In this grid integrated DC microgrid hardware test bed, the AC bus voltage is set at 110 volt RMS with 50 Hz frequency. Semicron IGBT stack, we can see here in the video, we have shown a single IGBT stack which has semicron switches and diodes. Before talking about the rating of the IGBT stack, let us look into the circuit diagram of the stack. It mainly consists of two sections. One is the three-phase diode bridge rectifier towards the left, and in the right it is the three-phase four-wire inverter bridge circuit. The three-phase diode bridge rectifier has the input AC voltage rating of 415 volt and DC output voltage of the rating 560 volts. The inverter bridge has DC input voltage rating of 700 volt and AC output voltage rating of 415 volt RMS along with 30 ampere output current. One important thing to be noticed here is that the DC input capacitor or the DC bus should be rated to more than peak of the grid voltage such that the power can be transferred from the DC side to the AC side. The basic understanding here that until unless you create a voltage difference, it is not possible to transfer reasonable amount of power from one point to the other. For 415 volt RMS AC grid, peak voltage is around 586 volt and the rating of the DC bus is 700 volt. This ensures that there is a sufficient margin for the inverter operation, and in our demonstration we kept higher operating margin by considering the maximum DC bus voltage of 400 volt DC and 110 volt RMS AC grid. The IGBT module used here is SKM75GB12T4. You can see here we have an IGBT module shown in the video, where in terms of the rating it is not same as the one used in the IGBT stack, but physically it look quite similar. Here one module can form an inverter leg, as each module consists of two IGBTs along with the corresponding body diodes. Hence, four such modules are used to form a four-leg inverter. The rating of the IGBT module used in the stack can block voltage up to 1200 volts and also can carry a nominal load current of 75 amperes. It supports switching frequency up to 20 kilohertz. These modules are attached to the aluminum heat sink, which can be seen here to dissipate the heat. These IGBT modules are popularly used in solar inverters, motor drives, as well as UPS applications. Within the stack, forced air cooling through fan is also provided for carrying out fast cooling. Also, in the inverter section, one can notice that each IGBT module is provided with the snubber capacitors. Those are connected in parallel to provide protection against the high dB upon dt. The trigger that IGBT switches gate drivers are required to convey the pulses received from controller to the gate terminal of the IGBT. Each driver can trigger one module. Hence, four numbers of Skyper 32R gate drivers are provided. And these drivers also require isolated DC input of plus or minus 15 volt to operate. Moreover, these drivers have inbuilt dead band protection as well. At the DC link input of the inverter bridge, we have earlier seen two semicron make electrolytic capacitors are connected in series whose ratings are 4700 microfarad, 700 volt each. Across each capacitor, bladder resistors are connected to discharge the stored energy in the capacitors when the inverter is not in operation. Apart from this, the IGBT module also has an inbuilt thermal trip protection feature in case if device exceed the threshold temperature. Let's talk about the detailing of the power amplifier operation. This is a power 4-quadrant amplifier. It is used to emulate AC bus or DC bus voltage by configuring internally or externally. For configuring it externally, the output voltage of the power amplifier is generally controlled by external controllers like RTDS or Opal RT. In this hardware demonstration, we have used Opal RT to control the power amplifier to emulate the DC bus voltage. Here, an external voltage signal is used to the analog input of the power amplifier in proportionate to the required DC bus voltage. The rating of the power amplifier is 22 kilovolt ampere, and it can be able to emulate AC bus voltage in the range of 0 to 300 volt RMS and DC bus voltage in the range of 0 to 800 volts. For example, the analog input voltage range is 0 to 10 volt, which corresponds to the DC voltage range of 0 to 800 volts. For getting DC 400 volt output from the power amplifier based on the DC bus voltage controller output, the Opal RT gives a proportionate DC signal input to the power amplifier to emulate DC bus voltage. In Opal RT, a PV and battery are connected to the DC bus. DC bus voltage controller is simulated, which regulates DC bus voltage based on DC side power generation. In this hardware demonstration, the rated DC bus voltage is considered to be 400 volts. We have used Hall effect based sensors for both voltage and current sensing. A LEM make voltage transducer LV25P is used for voltage sensing, while the current transducer LA55P is used for current measurement. Apart from these LEM sensors, the voltage and current measurement sensor circuit also consist of signal conditioning circuits and level shifting circuits. In this hardware test bed, the voltage sensor output voltage to input voltage ratio is 1 is to 100. That is, for the input of 100 volt peak to peak, the sensor output voltage is 1 volt peak to peak. Similarly, the current sensor's output voltage to input current ratio, that is 1 is to 10, means for 10 ampere peak to peak of current, the output voltage of the current sensor is 1 volt peak to peak. Further, the voltage and current sensor circuits are powered by using a DC source of plus or minus 15 volts. Let's look into most important part of this hardware demonstration, which is mainly the DSP controller. We have used a Texas DSP TMS320F28379D controller to control the inverter between the AC grid and the DC microgrid. The DSP controller is the most economical controller that is used for grid integration applications. For developing any rapid control prototyping, we need to configure the analog to digital converter ADC and PWM pins of the DSP controller. Generally, the DSP controller has 16 ADC pins of 0 to 3.3 volt input range with 12-bit resolution. It has direct 12 PWM pins for generating PWM signals at desired frequencies. Implementing a control system in DSP requires three-phase voltage and current signals along with DC bus voltage. The three-phase voltage and currents are measured through sensors. The proportionate output of sensors is a sinusoidal signal, which is a bipolar signal. This bipolar signal cannot be given to the ADC pins of the DSP controller because the ADC converts only the positive side of the signal into its digital form, and the negative side of the signal is always converted to zero. This causes a significant loss in signal. To avoid such situations, the output of the sensor is given to biasing circuits, which biases input signal above zero level, and the bias signal is given to the ADC pins of the DSP controller. These ADC pins converts the input analog signal into the 12-bit discrete signal. The control system requires 3 voltage, 3 current and DC voltage signals as input and generates the required PWM pulses to control the grid-tied DC microgrid inverter. These input signals are given to the programmed control system in the DSP controller, which generates the required PWM pulses. Here, the DSP generates PWM pulses at a voltage range of 5 volt. The switching voltage range of the IGBT present in the semicron stack is around 12 to 18 volts. The generated 5 volt PWM pulses alone are not sufficient to drive the IGBT switches. For efficient triggering of IGBT switches, the generated PWM switches from DSP are shifted to 15 volt by using a level shifter. Now the level shifted pulses are ready to give to the semicron stack to avoid grounding issues in the electronic circuit such as sensor circuits, biasing circuits and level shifter circuits are powered by a common DC source with different voltage levels. Hardware demonstration of the grid integration. Now before going into the demonstration, let us have a look at the hardware connections. The DC microgrid emulator, that is power amplifier, is connected to the DC input terminal of the IGBT stack. The AC output terminal, that is RYB phases, are connected to the L filter. Each filter box has multiple tapping from 0 to 10 millihenry. For each phase, we have connected two such inductor boxes in series to form total inductance for phase of 10 millihenry. The other ends of the inductor is connected to the point of common coupling PCC formed by this MCB. At this MCB connection, bulb loads are connected in parallel path and they act as a load to me. The other side of MCB is connected to the outside of the grid emulator, while the input side of the emulator is connected to the distribution system, which is connecting to our campus network. Also notice that after inductors, the wires are passed through the LEM current sensor. For voltage measurement, sensing is done near MCB input and the sensed signal are connected to the LEM voltage sensor board. Stress. Very good morning, dear friends. Today we are going to talk about demonstration of energy management in DC microgrid under the course title Smart Grid Basic to Advanced Technologies. Though some of the fundamentals we have discussed in the past, but today we will get into more details of this program, especially an application. In the previous module, we have seen the architecture of the DC microgrid and its grid integration. Further, we studied how to integrate a DC microgrid with the AC grid in that model. To understand the present module, energy management of DC microgrid, fellow students required the knowledge of the previous module. For this reason, we are repeating some critical aspects of the earlier module. Now, the module mainly focuses on energy management between DC and AC bus of the DC microgrid. This slide shows the block diagram of the L filter grid tied DC microgrid. In this slide, it is shown that the hardware testbed is developed by interconnecting various components. The AC side of the inverter is connected to the AC grid through L filter. The point PCC shown in the block diagram forms an AC bus where the AC loads are also connected. A Hall effect voltage and current sensor are used to measure the voltage and PCC and current through the inductor. The measured voltage and currents are biased to shift the signal above zero level. The offsetted output of current and voltage sensors are given analog to digital converter, so called ADC pins of DSP Launchpad TMS 320 F28379D. Inside the DSP controller, the ADC pins read the three-phase currents and voltages along with the DC link voltages. By using Clark's transformation, the three-phase voltages and currents are converted to the stationary reference frame from ABC to alpha beta, such as UABC to U alpha beta and IABC to I alpha beta. Further, the control logic generates modulation voltages for generating PWM pulses through EPWM pins of the DSP. These PWM pulses are used to switch the inverter. Now, the grid connected mode of operation. This slide shows the control logic used for interfacing the DC microgrid with the AC grid. The DC bus voltage controller regulates the DC bus voltage at the reference value and generates the AC power reference value. Active current reference is generated from AC power reference as the inner controller requires a current reference. The obtained AC current reference is converted to the stationary reference frame. This current reference is compared with the measured current, which normally gives an error. The error is processed through proportional plus resonant controllers for generating required modulation voltages. The modulation voltages are used for SPWM generation through EPWM pins of the DSP for switching converter switches, commonly IGBTs. The control variables of the PI controller as well as the PR controller can be obtained through proper tuning, ensuring that the stability margin should be more. Now, if you look at the laboratory prototype of the grid-tied DC microgrid, This slide shows the block diagram of the hardware test bed. In this hardware test bed, the DC microgrid behavior is emulated through a power amplifier by configuring it with Opal RT. In the Opal RT, the DC microgrid is simulated, which contains PV, battery, and variable DC loads. The scaled down DC bus voltages is given to be the analog input of the power amplifier. The current fed to this power amplifier is given to the analog input of the Opal RT. This creates a PHIL loop between the Opal RT and the power amplifier. The combined operation of the Opal RT and the power amplifier emulates the DC microgrid behavior completely. The behavior of the AC grid is mimicked through Synergia programmable grid emulator, Semicron 3-phase IGBT based PWM inverter is used as a bidirectional DC-AC converter between the DC bus and the grid. The control logic shown in the previous slide is implemented in the DSP controller. The floating point Texas C2000 DSP controller of the TMS 320F28379 Delfino type is used in this hardware test bed. Now, moving to the hardware demonstration, let us have a look at the hardware test bed. And this test bed is developed by interconnecting various components such as grid emulator, DC microgrid is emulated through Opal RT, IGBT stack, filters, DC loads inside the Opal RT, and AC load, which is externally a bulb load. In this hardware test bed, the DC microgrid is emulated through the Opal RT, which forms a DC bus. The emulation of the DC microgrid will be shown in the later part of this video. This DC bus is connected to the DC input side of the IGBT stack. The AC side of the IGBT stack is connected to the input side of the MCB through an inductor. The output side of the MCB is connected to the grid emulator. The bulb is connected at the MCB point, which acts as a parallel AC load. Most of the components used in this hardware testbed have been explained in the previous module. In this hardware testbed demonstration, we are interested in showing how to program the desired control system in the DSP controller through MATLAB embedded coder will be explained in detail. Further, the emulation of the DC microgrid through the power amplifier by using Opal RT will also be explained. Finally, a test case demonstration shows the power exchange between AC bus to DC bus of the grid connected DC microgrid. DC microgrid emulation through power amplifier using Opal RT with the help of power hardware in loop experimentation, so called PHIL experimentation, the DC bus of the DC microgrid is emulated through a 4-quadrant power amplifier. The DC microgrid is implemented in the Opal RT, which runs on RTLab software by calling the MATLAB Simulink files. The DC microgrid consists of solar, BESS, and variable DC load connected to a DC bus. This DC microgrid is initially simulated in the MATLAB. Now, the simulated DC microgrid is rearranged in the form of a master subsystem and control system. Master subsystem consists of power sources or control/computational algorithms. At the same time, the console subsystem consists of variables that need to vary time operation. To emulate the DC bus, voltage through power amplifier, the DC bus voltage is sent out through analog out of OPLRT by scaling down to 0 to 10 level, which is the power amplifier analog input voltage level. The power amplifier is configured to external mode, which gives the voltage corresponding to the analog input voltage value. Now, the analog output of the power amplifier is given back to the analog input to the OPLRT controller. This input signal is the input to a current source connected at the DC of the DC microgrid. Here, the analog output of the power amplifier is the current signal that either fits or draws from the power amplifier. The same current signal is either fed or drawn through a current source at the DC bus of the DC microgrid inside the RT lab of the OPLRT. This looping system between OPLRT and the power amplifier effectively emulates the DC bus of the DC microgrid. The output of the power amplifier is connected to the IGBT stack at the DC input side. The output side of the IGBT stack is connected to MCB, which forms an AC bus at which the AC load is connected parallel to the grid. Here, the AC load is a bulb load and the IGBT stack acts as an interface between the AC grid and the DC bus, which is called an interfacing converter. The control system of the IGBT stack is implemented in the DSP controller. Implementation of the control system in the DSP controller as follows. The voltage and current measurement are given to the DSP controller by using biasing circuits. The accessing of ADC and PWM pins of the DSP controller is explained in detail in the previous module. In this module, we are very much interested in showing the implementation of the control system within the DSP controller. Initially, the grid-tied DC microgrid is simulated in the Simulink and the corresponding control is implemented in the same Simulink. Make sure that this simulation should run perfectly. After simulation, remove the plant and keep the control system that is required in DSP. Configure the DSP launchpad at the hardware setting of the Simulink setting pane. Before configuring the launchpad type, ensure that the required softwares are needed to be installed in the system as per the guidelines given by MathWorks. After the configuration, the ADC pins must be configured to get physical signals into the DSP controller. Make sure that the ADC pin configured inside the Simulink is the same as the pin the signal needs to connect. The control system process the signals and generate modulation signals, which are used to generate PWM signals. These PWM pins need to be configured to take out from the DSP board. Now, moving to the hardware demonstration test cases, we'll consider the first case. As we know, the DC microgrid is emulated through the power amplifier, and the control system of the interfacing converter, which is between the AC grid and the DC microgrid, is implemented in the DSP controller. In this test bed, the interfacing converter has been given the responsibility of controlling the DC bus voltage, which is at 400 volts. The first test case that we need to observe here is if the sum of the power generated by the PV and BSS is more than the DC bus load, the power flow from the DC bus to the AC grid, and to achieve the above two phenomena and to demonstrate this test case, we assume that the power generated by PV and BSS are constant and the DC load is varied in steps. By looking at DSO, we can clearly witness that the decrease in DC loads increases the current magnitude. Looking at the power amplifier power sign, which is positive, means the power is flowing from the DC bus to the AC grid. Now, moving to the second test case, similar to the previous test case, the power generated by PV and BSS is less than the DC load connected at the DC bus. By looking at the DSO, we can observe the increase in the DC load reflects the current magnitude. Looking at the power amplifier power sign, which is negative, means the power is flowing from the AC grid to the DC bus. So, earlier it was DC to AC grid and now it is AC grid to DC bus. The DC bus voltage is always regulated to 400 volts. From these test cases, we have witnessed the energy exchange between the AC grid and DC microgrid. Now, moving to the references, all the test material which has been presented before you, we have referred the following references very closely. However, I also suggest you to refer important textbooks and many more references for your kind consideration. To conclude, we have experienced how to use a DSP controller in applications of grid integration of renewable energy sources and DC microgrid, etc. The significant benefit of this lecture is that the students can develop their own control system to control a DC microgrid with low cost controllers like DSP controllers. With this, we are coming to an end of today's lecture. Thank you for your kind attention. Thank you. Students, am I audible? Am I audible? Wait. Am I audible? Yes? They're saying yes? Okay, very good. So I think today's lecture is slightly important. Not today, I mean almost for last couple of lectures are very important because we are slowly touching upon all the measure devices, like, partly RTDS simulation, and today we talked about OpenLAT simulation, use of power amplifiers, and rest all are actually very basics, and grid emulator, isn't it? So these are the major components. So I think if you wish, probably you can develop your own setup in the laboratory. Probably not in hurry, but if you have those equipments, so I can strongly recommend that a reasonable economic version of OpenLAT and grid emulator, if you have, well and good. Even without that, you can do most of the simulation. Couple of inverters certainly mandatory. And the advantage of OpenLAT, what we have experienced from RTDS, with reference to RTDS is expensive, no doubt about it. And then you have actually, RSCADE simulator. But the OpenLAT is capable of taking MATLAB codes directly into simulation. So if you like to handle any large system or already some programs you have carried out in MATLAB, they can be burned into OpenLAT easily. That is one advantage we have seen. But there are certain accuracy challenges that scholars claim that, RTDS is much better compared to OpenLAT. So both have their merits and limitation. So we will not take a call which is better, which is not. But what we wanted to highlight that actually any simulator, any grid simulator, and with a basic DSO and inverters and few sensors, I think probably the DC microgrid setup is possible. So what is the journey if you see what is happening? I mean, almost if you see, we are talking about microgrid all the time. But slowly we started with the philosophy. Then we went to actually DC, then AC, then hybrid, then RTDS simulation, then real-time simulation, and then CHIL, then PHIL. And then these are the applications, couple of actually applications we are talking about. So that is how the journey is all about, am I right? So it looks very simple, but if you wish to realize it in reality, it is not that easy the way it looked like. But it is easy once you actually try to grasp the concept so very seriously. So if you see the second half lecture, almost first couple of sites were repetition of the previous lecture. But I was not feeling bored because I was thinking that it would have been repeated even 5 times. Because those who miss some points in the first time, it's not enough. In one hearing, you will remember everything. So you need to listen to this actually not one time, 2 times, but at least dozen of times, 10 to 15 times to make sure what has been told. Okay, so first time you'll each and every component, until unless you go to the lab and put it in ground, I mean, your story is not complete. So, but I'm confident at least some of you will be successful in hardware implementation, but all of you will be certainly successful in the simulation part for sure. So, with this note, thank you very much and wish you all the very best. But if you have any questions, please do ask us because we will be left with another 2 days more. But the journey was quite satisfactory because I could see the attendance is very constant, It is not fluctuating. It is going exactly the same for last 8 lectures, which is a big achievement, I can say. So thanks all the participants for your time and I hope you have enjoyed. Uh, I mean, just any suggestion or any comments? Are you scared of these hardware demonstrations or you are enjoying? How do you feel about the hardware demonstrations? Any one of you? Chandrasekhar? Oh, they're saying yes, sir. Okay, they're enjoying or? Okay, informative. Anybody else? Very information, sir. Okay, good. I think you please, keep on learning. I'm very sure in a couple of times, if you listen to the talk, you'll be in a position to enjoy more. Uh, yeah, demonstration was very good. Okay. I think thank you very much, and probably we'll meet again on 5th and 6th. So next lecture will be on 5th at 5 p.m. Am I right? That is Tuesday. Huh? So Wednesday we'll have the concluding sessions. Examination, do you like to take one more test for them?
Yes, sir.
Which day?
Wednesday.
Wednesday, the last after the end of this. Okay. So thank you very much and take care.